Welcome to this Xendee University conference on why microgrids now, achieving speed to power for AI data centers. My name is Adib Nasle. I'm co-founder and CEO at Xendee, and I'll be the moderator with an incredible panel of experts, Amir, Jim, and Mike, that will be bringing their knowledge and experience to the table. Amir Kiani is a senior technical program manager at Amazon Web Services, or AWS, as we call, and he's been focused on on-site power generation, microgrids, advanced energy solutions for data center infrastructure. So very relevant to the topic that we're going to be talking about. And he spent a lot of his career in a clean energy space in technology, R&D, product development, commercial strategy, and large-scale deployments. So we look forward to his perspectives, bringing a practical view on how microgrids and on-site power solutions can accelerate speed to power for AI data centers. And we're also joined by Jim Walsh. He's Vice President and General Manager at GE's Vernova Consulting Services. And he's leading a whole global team of power system experts that are helping everyone from utilities and grid operators and developers and large energy users really navigate the space and address some of the most complex challenges. So there's a lot of expertise that's coming to the table for our conversation together. And Jim brings over 3 decades of leadership experience, a lot of experience also from the technology and software and automation of energy systems. And we also have Mike Shepard from Mainspring joining us as well. And Mike is Director of Data Center Business Development at Mainspring Energy. And that's Mainspring's linear generator technology, actually one of the innovative solutions that I'm personally interested in learning more about. And he leads the development of on-site power systems for data centers for Mainspring's customers. And he also brings over 2 decades of experience in this on-site energy space, including 6 years at Bloom Energy, where he led the hyperscale executive, deep building expertise and on-site generation. So we're going to have a pretty good conversation. But before we get into that conversation, I got to just give a little overview here around the fact that the views that are being expressed by our panelists during this discussion are solely their personal views and opinions. So they're not going to represent and should not be interpreted as representing the official position or views or endorsements of Amazon, GE, Vernova, Mainspring, or any other affiliated organization. So with that out of the way, I have a question. I'm going to start the first question. Up until recently, energy used for computing has not been a big deal, maybe a 0.5% growth per year. But all of a sudden now, data centers are on the news every minute, and they're coming online with this incredible level of sustained demand that somehow, at least the impression I have, wasn't anticipated by the utilities or policymakers. So I'm going to ask the panel, why the lack of foresight? Well, and Amir,
Listen,
you go first. I'm
Sure,
volunteering you to go first.
Yeah, sure, I can start. Thanks for the intro, by the way. Glad to be on this panel, and thanks to Xendee for organizing this. To answer your question, in my view, I don't think there was purely a lack of foresight. In fact, for years, the efficiency gains in the data center technology space kind of masked the growth in compute demand because hyperscalers and data center developers kept adding compute, but with better chips, better utilization, and better data center design that is more efficient than our previous generations. So that kind of helped keep the power growth manageable for utilities. As you all know, and all the participants know, by the launch of ChatGPT and growth of AI, that has changed quite a bit. The main reason is the loads that that these AI large language model require are now larger, more dense, more concentrated, and they're needed much faster. And on the other side, the utility planning is built around gradual, visible demand growth. So what happened was with the launch of AI and the growth, AI kind of introduced a step change in the demand. And oftentimes these data center projects are confidential projects, and the timelines are uncertain. So on the utility side, the planning system was looking in the rear view mirror while the compute market was accelerating significantly in the real time. So that's how we are in this situation. And yeah, happy to hear others' opinions and inputs on this as well.
Yeah, Jim, or Mike, do you guys kind of
Yeah.
have
I
a
think,
view into this as to how
yeah,
kind of it seems like some people were caught flat-footed on this?
yeah, I think it feels a little bit like we're all playing a bit of catch up here, maybe with the exception of the hyperscalers. But I think Amir hit, from my perspective, the most critical point, which is it's easy to look at two data centers side by side, one being a cloud-based data center, the other one being an AI training data center, or even AI inference, and make an assumption that the load is similar between the two. They're both fueling compute, et cetera. The reality is the loads are materially different. The amount of power density that's required for the AI training is meaningfully different, much, much higher than it is for cloud compute. And so I think that's one of the elements here that is driving sort of an order of magnitude difference. I think the other thing, and it's really quite a tribute, frankly, to the hyperscalers, is the speed by which the models have advanced. I think for those of us, maybe with the exception of those that were really, really intimately close with AI, we saw AI as this promising capability on the horizon. And in a matter of what felt like seconds, it was upon us. And not only was it upon us, but the maturity, the speed by which these models have matured, and the uptake that has taken place in companies like mine, I think has exceeded anybody's even most aggressive projection. So you've got the backdrop of what Amir talked about, which is we've got a power system that has grown very, very incrementally over the past number of decades. All of a sudden, you've got a new load that is super dense, requires lots of megawatts in a confined space, and there's a massive amount of uptake in the technology. You put all those things together, and I think you end up a little bit where we are, which is a lot of excitement, a lot of activity, but all of us feeling a little bit like we're trying to catch the bus here.
Yeah.
I'll follow up to that. And Adib, thanks for the intro and for including me on the panel. I think Amir said it very well when this is a step change. So we have had that incremental growth for decades. We have not been maintaining our poles and wires. So that's been going one direction while the demand is going another direction. And if you just look at, NVIDIA 10 years ago, they had a market cap of $18 billion. So no one really saw this coming. Anyone who did would be very rich with NVIDIA stock right now. But the growth has just been absolutely unprecedented. Unprecedented doesn't even seem like a big enough word for this. If you were to bring up, gigawatt scale projects 5 years ago, you'd be laughed out of a room. And now people are talking about 10, 20 gigawatt projects. So it's not, you can't blame the utilities. You can't blame, any one party for how we got here. It's just an exciting time to be helping, address this issue.
So Jim, you said just a few minutes ago that it was like a step change that happened almost instantly or very, very rapidly. How have you kind of viewed or seen the urgency around this need to get to power as quickly as possible change over the last, I don't know, 18, 24 months? And what has been your experience and what's really driving the compression of these timelines?
Yeah, it's a good question. And just by the nature of the question, I know that part of the answer, which is that the urgency feels like it increases every day. And there's a number of reasons for it, but I think the headline likely is that speed to power used to be kind of an execution metric that we would use in maybe times of more incremental build out. Whereas now, if you're talking to the hyperscalers in particular, what they're saying is it's an absolute strategic advantage. And if you maybe double click one level down to say, well, why would that be such a strategic advantage? I think there's a couple of vectors. One is again, as I talked about, the uptake has been maybe beyond people's expectations, and so there's a true revenue opportunity on the table for the hyperscalers. But I think the other element of it is just by the nature of how an AI training or an AI model works, the more time you have it in play, the better it becomes. And so if you've got a lead on your competitors in terms of the capabilities of your model, the way the model improves is through additional exercise and use. And so, when you're talking about AI, you need three basic things. You need the model, you need the silicon, and you need power. The models are really well established. The chips are well established, and now the hunt is on for how do we get power as quickly as possible? How do we bend the curve in terms of what the traditional path has been to get power? Because in so doing, again, you take advantage of the shorter and medium-term revenue opportunities, but you also make your product better. And I think that's really a big part of what's driving things.
Yeah. Amir, you're at the tip of the spear on this yourself with the work that you're doing at AWS. How's your view changed over the past year or two around these timelines and the urgency that Jim was just touching on?
Yeah, great question. I think, as Jim mentioned, these AI models can change very quickly, and whoever gets ahead of everyone else to train these models is going to be having a better model and better output and more customers, more revenue. I think I saw this in a presentation by NVIDIA. When you look at the supply chain of these data centers, there was like a pyramid with everything that is needed to build an AI data center. I think as people look through different layers, they're understanding that the bottom layer is power and energy that is required to train these models. And there is more and more focus on that bottom layer because you can build the shell, but without the bottom layer, which is power, you cannot really do anything with that cold shell. So there has been more focus on my team at AWS, which is the Power Generation Solutions team, on how we can remove that barrier from the whole ecosystem. And as leaders in these organizations and also these AI startups understand that problem, I think the need for power and energy and innovative solutions when it comes to behind the meter power generation has increased significantly. A few years ago, my team was not getting this much attention that we are getting now. So it's a good and bad thing at the same time. But yeah, everyone in hyperscaler world understands the urgency, and it has changed quite a bit over the last 24 months.
So with these behind the meter solutions and the urgency, and just the timelines, and based on what I'm hearing from Jim and yourself, it's also really a business critical piece of being able to execute towards the strategy and have a competitive advantage. And Mike, I'm curious how Mainspring is playing in this field. Obviously, you have very novel technology that addresses several value streams, but when it comes to these timelines, how are you guys kind of supporting that foundational layer that Amir was talking about, that you got to have that power, otherwise you just got this cold shell that isn't doing anything? How are you guys really engaging with the stakeholders in this?
So, I mean, just quickly on the last 24 months and how things have changed. 2 years ago, I think we were seeing, more about sustainability and, how that plays into the future. And everyone's got their green goals that are 2030 or 2035. I think that's taken a bit of a pause, and it's just all out, like, how do we get power on board as quickly as possible? And then another big change in the last 24 months is specifically how to address AI data center loads. Before, it was just anything behind the meter, give us a generation, flat loads, basic load following. You don't need to have these wild swings multiple times per second per minute. So being able to address these loads by, providing a complete solution that, thermal technologies, and Jim can probably attest to this as well, thermal technologies cannot do it on their own. So we need to be able to partner with others like batteries, supercapacitors, to be able to address these loads and provide an overall solution. And then to your second question, just on how we are engaging with communities, it really depends on, where we are and what the community is most interested in. We have a solution that doesn't use any water. We know that there's some misinformation in the public view about how much water data centers use. So if the community, if we're in Arizona, it's going to be discussions about water use. If it's in Utah, it's going to be discussion about particulate matters and smog. If it's in Chicago, it's going to be discussions about noise in the neighborhoods. So it's really getting a read on the community and, figuring out what to address and getting ahead of it before you start announcing big projects.
Yeah.
This is something that AWS has done very well, creating green spaces, creating parks for the community, and having their best foot forward before they go into these communities. So that's how we like to think about it. You just try to get ahead of, any potential pushback, any misinformation that's out there about what data centers are going to do in the community. And just one other piece, islanded operation is going to help alleviate some of those concerns about rising electricity rates.
Can you guys speak a little bit to the water usage? And I bring that up because it's like in the news, like every 5 minutes, and people are protesting, and there's a lot of anxiety when somebody announces a big data center, and people think, like, all of a sudden all the water in their state's going to disappear. Can one of you speak to the water piece that's seeming to be of concern, in addition to obviously the noise and air pollution components that people sometimes bring up with these large campus data centers?
I can speak to that a little bit. I think when it comes to water, as Mike mentioned, there is some misinformation as far as how much water is being used. I think there was a metric a few years ago, or like when ChatGPT was launched, that like every prompt is a drop of water. And a couple of major hyperscalers put out white papers that this is in fact not true. So taking a step back, why do we need water for data center? Majority of it is for cooling the racks. If we have on-site power generation, which is not widely used right now at data centers, you will need some additional water as well. but as the cooling technology is evolving, and Amazon has a separate org, AWS has a separate org that is working on liquid cooling specifically. I think the demand in water usage is gonna be less and less. The industry of liquid cooling, I'm no expert in liquid cooling, by the way, but the industry is moving from like an HVAC type cooling for the racks into like a localized direct chip liquid cooling systems, which are way more efficient in water usage. And there are other technologies that are reducing that. So maybe old data centers use water less efficiently, but when it comes to hyperscalers, this is one of the sustainability metrics that we're using. There's also talks about when we say water, which type of water are we talking about? It's not all like drinkable water that we are using for data centers. There's also gray water that's being used, and Amazon's goal right now is to be like water neutral. And there are some other technologies that can be used to actually like generate that water on site as well. That's kind of like a down the road. The technology is not in the right TRL right now, but I think there is misconception as far as the water usage, what type of water, and the community impact. But hyperscalers response shouldn't be like rejecting community concerns. I think there needs to be work with community and kind of earning that trust in this data center space to have successful projects and community buy-in. So
what about absorption chillers?
Yes, yeah.
Yeah, that's addressing it too.
Yes, absolutely. Like I think there are things that we can do inside the data hall or where the servers are, and that is getting the heat out effectively from the chips. And there are other things that we can do outside the data center and dissipating heat to the environment more efficiently, like absorption chillers.
So when we're thinking around this whole behind the meter ecosystem, Jim, when it comes to these large power users and hyperscalers wanting to get electricity as quickly as possible, but there's this concern about cost shifting, and then there's a reliability risk, and then of course there's emission. Can microgrids help folks get energized faster without shifting the cost, so the ratepayers aren't bearing the burden? And where do you see it from a risk and even an emissions perspective based on the work that you've been doing?
Yeah, listen, it's a great question, and it's a really salient topic, predominantly based on what you suggested around and what we talked a little bit about how important speed to power is. I think you have to start with the reality that behind the meter microgrid type solutions do give you an opportunity to get first power faster. It will typically be at a premium cost, but what we're seeing is that in some cases hyperscalers see enough value in time to first power, enough monetizable value that it more than offsets that premium that you're going to pay in the short term for a behind the meter solution. And the reason it's more expensive, as you might imagine, is you've got to build in more redundancy. It just as one example, because you don't have a backstop of the grid. What we're hearing most of the time is, rather than it being a debate around behind the meter or grid connected, most of the behind the meter discussions that we find ourselves involved in tend to be around how to bridge until you can get a grid connection. And just for context, and you likely know this, but generally speaking, with the interconnection queues the way that they are, you're typically talking about sometimes 5 to 7 years in terms
Yeah.
of getting a grid connection at the sort of scale that you need. And oftentimes there's transmission investments that need to be made, et cetera. That said, and certainly not speaking for all the hyperscalers, but what I will tell you is way more often than not, I think the hyperscalers ultimately desire a grid connected solution. It offers the benefits of the whole power system, the reliability, the power quality, and so it seems rare that when we're having discussions to people about starting islanded and staying islanded forever, instead it's much more of a bridge. And so then the question becomes, look, how do you do it the most efficient way, knowing that you've got a grid connection coming down the road? So that's kind of the way I describe the dynamic that we're seeing and feeling right now.
So where do you guys see the story kind of evolving? I mean, you talk about it being a bridge solution. Is there a story here around how the microgrid and its assets become permanent architecture for AI compute and not just a bridge solution? And is there a risk where the customer implements a microgrid, gets very comfortable running their own power, gets very comfortable basically operating also as a small utility on site?
Yeah.
And let's say 7 years later, the utility brings the capacity in for you. It could, I mean, do you foresee the data center folks saying, yeah, we're not going to use this anymore, we're going to actually pay more and connect to the grid? Or is there a risk for the grid upgrades to become a stranded asset, or is there a risk for the on-site generation assets to become stranded? Where do you guys see this? And I'm opening it to all three of you.
I'll jump in. Or Amir, you want to go ahead?
Yeah, go ahead.
So I mean, a lot of the conversations, and the growth of Mainspring and also Bloom and other on-site generation technologies has come from the lack of the ability of the utility to serve all these loads. We would not be having these conversations if AWS could just go to their local utility every time and say, we need 500 megawatts. So we're very much in the conversation, and you are correct that they're talking about it as bridge solutions. So it is that 5-year time frame that Jim mentioned. But in terms of what happens after that, I think depends on a few things. It's really like the track record of the assets. I mean, are they capable? Are they experiencing any downtime? Are they performing as expected? Also, where in the world you are. I mean, if you are producing cheaper electricity on site, cost does matter. So if you're in California, if you've got 20-cent power from the grid and you're producing 12 cents on site, then that's going to be part of the conversation. And then just the idea of a stranded asset, I think another consideration is just what can you do with those assets after 5 years if you're not going to use them for continuous baseload power. Can you use them, as a bridge at another site? So it's essentially bridge to bridge, or you could do bridge to backup if you have, technologies that can start in under a minute. It could be, a viable solution to replace your diesel gen sets.
I had a few sentences from like the hyperscaler point of view. I think for us, when it comes to the point about a stranded asset, I think for having on-site power generation microgrids, even as bridge solution, is costly. It adds a lot of scope to our scope compared to utility, because we have to own and operate assets on site. But if you think about the cost of waiting, sometimes that cost of waiting or lack of revenue offsets the cost premium that we pay for microgrids. in some cases, in some data centers, that revenue capture might pay for the whole cost of the on-site power generation, which means like after like 3 to 5 years, if you look at it as a bridge solution, you might be able to like kind of replace that to another site or add to the campus by having like a phased approach. There are also other concepts around what can you do after that transition period with the on-site microgrid. Can you use them as a backup? Can you convert that prime to backup arrangement with these assets? Can you use them as demand response? Other things that are also going to add to that financial analysis when it comes to having these assets as a transition to grid. The point is, I'm not advocating for off-grid data centers with microgrid everywhere. I think the question is not grid versus microgrids. I think it's going to be microgrids complementing the grid as a permanent solution. And we're seeing more and more of that with the new campuses as we work on like the expansion and site selection.
Interesting. Jim, are you seeing a similar trend as well?
Yeah, we are. I think the other element maybe to include here is that the overall load growth requires more generation than exists today. If you look at reserve margins, especially in the US, and you overlay that with what is sure to be load growth at an accelerated pace. I do believe that there will be a home for the generation assets that are being put in place now, whether it's part of making the entirety of the power system more robust or peak power, whatever the case may be. Because again, I think the misconception here a little bit can be that all of the load growth we're talking about is a function of AI training loads. And that's certainly the headline right now. But if you look beyond that, we're also seeing load growth at an accelerated pace in places like cloud data centers. Those continue to grow based on new applications, application use. You look at the electrification of general industry, whether it's transportation or some forms of heating, are moving much more to electrification. And finally, you see onshoring of industry happening at an accelerated pace, right? And so you put all of it together, and I think we're in for a reasonably long season of load growth that's different than what we've seen certainly in the last 20 years. Again, AI is a headline to that story, but even without AI training, there will be meaningful load growth. And so I think the investments that are being made now in incremental generation, be it as part of the broader system or even behind the meter, I think there will be a place for them as we, as a nation, continue to need more and more electrons over time.
Yeah, we've been seeing this broader trend that you speak of as well, with the onshoring of manufacturing and pharmaceuticals and obviously the compute load growth. But the one question I'm still debating is if, like, Amir, like if you pay the cost premium and you have a microgrid and it's working and it's meeting your load, what is the grid upgrade then for? And why should the ratepayers pay for a grid upgrade when at some point the workflow, the processes, everything has gotten comfortable just with co-located on-site power systems? Is it just behavioral, or is there an economics to it, or what's and Mike and Jim, feel free to chime in as well. But if your on-site system is working and is doing what it needs to do, and you got your costs to where you want them, you have your redundancy and your resiliency, why then the extra money and the many years and trillions of dollars to do the grid upgrades?
Yeah, that's a really good point and a good question overall that hyperscalers need to respond to. I think it's going to be case by case in many regions that we have data centers in. To your point, and I'm sure you can calculate this with Xendee, the LCOE of a microgrid might end up being lower than your tariff.
Yeah.
And that is like an NPV positive project. But I think from the operator's point of view, it's the operating and maintaining those assets is one area that we need to, as to my point earlier about the additional scope with microgrids, we need to take care of. I think that's not a huge blocker. We can definitely address those problems, run kind of like a power plant. The major one that is a topic of discussion is the availability of microgrids versus the grid. When you are running a cloud infrastructure, you're looking at 6 nines for your uptime. It is practically possible to get the same availability with a microgrid. But it means more redundancy, more capex, and a more complicated microgrid. So I think the availability and complexity is another aspects that we need to consider. Going back to the bridge solution, I think there is appetite among hyperscalers to accept a lower availability for like 2 to 3 years with the utility plan as providing higher availability. But yeah, I think it comes down to the operation of the hyperscalers and what they are willing to accept and what is a turnkey solution versus not when it comes to microgrids versus utility and LCOE.
Okay. And what is the the panel's been talking about this cost premium, but what is also the timeline advantage that you guys have been seeing, a realistic timeline advantage versus waiting for the grid? I mean, how is it sounds like it's material enough, and earlier you'd mentioned the cost of time to not actually get energized and not have that work being done. But what is that timeline advantage over a grid tied connection when it comes to a behind a meter solution? Is it years of acceleration, or what are we talking about here?
I would say it can be years. It can be, call it 2 to 3 years in some cases, right? If you're thinking about, the answer is obviously it depends on all these things, but if you're just using a 5 to 7 year average on grid connected infrastructure, and you're looking at a project that's going to take you 3 years from start to energizing, you're talking 2 to 3 years in that particular case. Obviously, mileage will vary depending on the driver, but it's meaningful enough to certainly warrant conversations and contemplation, which is what we're seeing.
I mean, if you look through, just public filings, what's out there, you can get to some level of revenue per megawatt installed. And if you look at grid costs, or if you look at behind the meter solution, we're lower. A behind the meter solution from GE Vernova or Mainspring is going to be a lot lower than that revenue generated per megawatt. So if they have no grid connection, we're not comparing ourselves versus the grid. We're comparing ourselves against, not having to compute at that site.
But even if there is a grid and your LCOE is lower by generating and managing your own energy, why would a customer still say, no, I want to pay more and get grid connected at some point?
From my experience, from my conversations with customers, they have that word from the utility saying they can get power by 2030 or 2031, 2029, whatever it is. But instead of, switching all over to the grid and leaving a stranded asset, they're going to use that power to continue to expand their operations.
Yeah, and we've seen something similar where, the initial need is so much power, but there's a significant load growth forecast that needs to be addressed. And even if the infrastructure comes in, is it still under capacity? So that we've seen similar trend as what you're sharing, Mike, as well.
Yeah, we all need that crystal ball, but I think the demand is going to continue to grow. And I don't foresee the grid keeping up with AI growth for some number of years.
So there's a flexibility here that's also, it sounds like, is important with the behind the meter solution, whether it's at some point going to get grid connected or not. It seems like, given the growth projections and the forecast, that there's always, you need a shock absorber in there to help you continue growing the business while the grid is catching up. And it sounds like there's a time variance here between how quickly the larger infrastructure can move versus the business side needs of individual organizations and companies. And until things settle down, to give a chance for the macro grid to catch its breath and catch up, sounds like that's going to be a while. Is that an accurate assumption, you feel, or is a lot of the projections maybe too rosy, and maybe the adoption isn't going to happen and the workload isn't going to be there? And I know we talked about a broader trend that's driving this load growth projections, but is there a risk here of overshooting and investing in, whether it's grid upgrades or whether it's behind the meter assets, and then you really might only end up needing a fraction of what you've built out for?
Yeah, that's I think we all need the crystal ball to predict what will happen with the AI training and AI inference in the next 5 years. I think companies will overshoot a little bit as far as what is needed for these large language models. I think we are all learning about how they behave when it comes to power. There are large load swings when it comes to AI training that I think everyone is dealing with. Whether the solution for those large load swings is to add more power or somehow manage it inside the data center, that still remains a question. But as far as like the demand, I think there are 3 layers that are going on top of each other. One is AI training. I know over the next 12 months to 24 months, that's going to remain a huge demand. Because a lot of these frontier models are still in the training phase, and they need more data, more clusters to come up with better models. To Jim's point, the cloud growth is still there. We are still using analytics. It is needed for cybersecurity. There is a growth in robotics that requires that. And then I think the last piece, so there is AI training, natural cloud growth, and AI inference. I think that AI inference highly depends on how AI gets integrated into our lives and um, uh, how often we use it for coding, enterprise applications. I think there might be a little bit of overshoot, but these data centers can change applications and customers. So in single data centers, we might have thousands of customers. And as a hyperscaler, you need to be able to adapt to these uh, different compute demands and how they might change down the road.
Yeah, no, that's the being able to change their workload. That's very astute.
You know,
Jim,
Adib, just maybe to add on here a little bit, I think it's a great question. It's one, as you might imagine, I'm guessing Mike spends a lot of time on this topic as well, but in Vernova, it feels like we spend 50% of our time trying to figure out kind of what the future model looks like in terms of demand, electricity demand. And what I'll tell you is, we not only seem to have developed a stronger conviction, but in the last couple of years in particular, we've been updating our most aggressive models up and to the left, up and to the right, I should say, in terms of demand. I mean, we just see, we just don't see or feel any short-term relent of this demand spike that we're seeing. Whether you're looking at our backlog, whether you're looking at projections of everybody that's trying to put models in place here, whether it's based on listening to the aspirations of our customers, there's a lot of still molecule-based power out there that is ripe to be transitioned from molecules to electrons. So there's just we don't think that there's a ton of risk in the short term that our models are too aggressive. If anything, we tend to be on the side of continuing to tweak them up and further out into the future than previously. So for what it's worth, again, it's an area we spend a lot of time on, and it really does feel like we're in a super cycle of electricity demand and therefore build out.
Mike, you're literally in the generation business, so I mean, how are you guys viewing this? And
it's an exciting time. I'm very, very happy with where I am right now. Yeah, no, we have all of our own projections, and Jim, that's an attractive backlog that you guys have. We're aiming for that ourselves. But we are always, looking at our customer orders, looking at what's in, contracting and deciding on, how big we're going with our manufacturing expansion. But we don't see any short-term pullbacks. I think everyone needs more generation on site, and it is going to be the answer for, the foreseeable future. I mean, the grid's simply not going to get there. And then talking about, how you get those electrons. Yes, you could do solar. Yes, you could do batteries, but they're not going to be addressing gigawatt loads. Okay. So we're going to need thermal generation for the foreseeable future here.
All right. So it seems like everybody is in agreement on not only the magnitude, but also the sustainability of this load growth demand. So that's very good. That's good to hear, because I think that shows a lot of economic growth opportunity as well. I was planning on asking a few more questions, but we got a ton of questions from folks in the audience, so I want to reserve at least 10 minutes. I apologize to the folks asking questions. I don't think we can get through all of them, but we'll get them answered offline for you as well. But there's one here from James Dodenhoff. It says, for the hyperscaler panels, I agree with the comment that data center operators have aggressively pursued computing efficiencies over the past 10 to 20 years to maximize computing capability per data center footprint. However, doesn't that call into question the current claims by some hyperscalers that they can deploy flexible demand practices in order to manage the data center energy supply demand balance?
Amir, you want to take a stab at that one? Or I'll chime in with what I can.
Sure. Uh, I think to answer that question, like there is that flexible demand that AWS has. I'm talking about AWS as far as like availability zones and how they can maybe move some of the compute between different availability zones. I think my point about like the efficiencies in the data center was mostly around there was there was demand growth when it comes to power, but it wasn't as aggressive as what we are seeing with AI. There is definitely that um, uh, growth naturally with cloud and all the other non AI applications that we have. Um, but yeah, it's I don't know how to answer from the hyperscalers point of view, but I think those practices are still in place and they're happening. So, Mike.
Um, yeah, I mean, for some areas of the country, like ERCOT, they're requiring that you have some level of flexibility, that you have some batteries on site. But also the chip makers are making, basically building in curtailment ability that allows the hyperscalers to unlock more capacity from the grid. So everyone, this is going to take every level of the AI stack to help unlock that capacity and make sure we're not, overburdening the grid. So I know the hyperscalers are doing it. I know individual areas of the country are doing it, but also the chip makers. So I mean, everyone recognizes that is a problem to be addressed. So I think that's just one of those things that's going to take all of us.
Okay. There's another question here. From an energy standpoint, what's the difference between inference and training data centers? Do we need to build inference data centers? And why training data centers must be large and same facility? Is there a world where inference becomes smaller plus distributed?
Yeah, I can take a stab at that one. I think starting with AI training for these models to train properly and build that neural network, they need much larger clusters. So you might require one data center, which is like a gigawatt of power for one of Anthropic models to get trained on. It's just the nature of the amount of data and the amount of training for those neural networks to develop that is required. Um, the difference between when it comes to energy, the difference between the training versus inference is significant. Um, I mentioned that there are some workload behavior that are atypical to any kind of data center load when we are talking about AI training. And this comes because of multiple reasons. As of now, a lot of these chips are GPUs, and GPUs are not specifically designed for training. There are other chips that are designated for training, like Trainium that AWS has developed. Those workloads will probably be more efficient and more towards a more manageable training load. To answer your question about whether a data center that was used to training can be used for inference. That is the exact model that I think is going to happen down the road. As you train these models in huge data centers, you might, which is training is a non-revenue generating mode, by the way. You might designate portions of your data center to focus on inference or use them as for inference, and then that ratio might change down the road as your inference, which is a revenue generating operating mode, gets more and more demand. So I'll be brief because I know we have 5 minutes.
Yeah. So I'll use that to ask one last question from another audience member regarding stranded assets. How much do you factor in the risk of having outdated technologies when you deployed equipment for temporary time periods while you waited on the availability of grid power?
I think there's a deep, long technical diligence process that takes place before they're going to deploy any of these assets. And they think about them on the timelines that they need them. Just speaking they as large hyperscale developers. So Mainspring has a product that is certified for 20 years. That's going to produce power for 20 years. It's described as doing what it's going to do. So if you just need electrons, we're going to be there to provide electrons. One thing, I mean, with the power side of it, it's a lot easier to stay relevant than using a chip that might be 5 years old.
Yeah. So the stranded asset risk is more on the chip side, probably because every so many years the upgrade cycles are so aggressive and so from just exponentially better. But when it comes to, would it be fair to say when it comes to how you generate and manage the power, that those are more enduring and not so susceptible?
I would agree. I do think that's the case. And I think it's a really, really good question. But again, most of the generation assets we build for this space are designed to run 20, 30 years. And we try very hard to construct them in such a way that they're relatively modular in design so that you can continue to contemporize the technology without ripping and replacing the whole unit, right? And so I think as long as we continue to do that, and again, as Mike said, there's a lot of diligence that goes in on the front end to make sure that what we're putting in place is going to line up well to the serviceable life that people are looking for. I think we can at least take some steps to minimize obsolescence by virtue of modular designs. If we've got to switch a part out because there's a new technology that is way more efficient or way more cost effective or whatever the case, that modular design enables that.
Yeah. And that's the inherent flexibility probably of microgrids too, that modularity.
Yeah.
You were going to say something, right?
I was gonna say this is the beauty of microgrids is the modularity, and you start with the technology and you keep the technology there, but you can augment that technology with storage, with renewables, other things, because you have a microgrid on site, and you can manage the energy flow between new technology versus assets that are supposed to be there for the next 20 years.
Excellent. Well, I'd like to thank all of you for your insight, the experience that you brought and shared with the audience today. Thank you so much, Amir. Thank you, Mike. Thank you, Jim. It's been a pleasure being in conversation with the three of you. And also to our audience members, thank you for the questions and for the engagement as well. And we will get back with some of the answers for many of those that we weren't able to address during the Q&A session here. But really appreciate the conversation. I learned a lot, and I hope the audience enjoyed and learned a lot as well. And I want to thank you again and look forward to additional panels on Xendee's University Week conferences. So thank you, everyone.
Thanks, Adib.
Adib.
Thank you.